Neutron stars are among the most extreme and fascinating objects in the universe, formed from the remnants of massive stars after a supernova explosion. They are incredibly dense, with a mass comparable to the Sun, but compressed into a sphere with a radius of about 10 to 20 kilometers. Here's a comprehensive overview of everything known about neutron stars. Neutron stars form during the death of massive stars that undergo a Type II supernova explosion. When a star with a mass of 8 to 20 solar masses exhausts its nuclear fuel, the core collapses under gravity. If the remaining core mass is between approximately 1.4 and 3 solar masses, the force of gravity overcomes electron degeneracy pressure, and protons and electrons combine to form neutrons. The result is a neutron star, a dense ball of neutrons. The core collapse is so intense that the entire star is compressed into a small, dense remnant, with a density exceeding that of atomic nuclei. Neutron stars typically have masses between 1.4 and 2.1 solar masses, but this varies slightly depending on individual cases. The upper mass limit is known as the Tolman-Oppenheimer-Fokoff limit, beyond which the object would collapse into a black hole. Despite their mass, neutron stars are incredibly small, with radii ranging from 10 to 20 kilometers. For comparison, the Sun's radius is about 696,000 kilometers, meaning a neutron star packs more mass than the Sun into an object about the size of a city. Neutron stars are the densest observable objects in the universe, with densities ranging from 3.7 times 10 to 5.9 times 10 superscript 1 kilograms per cubic meter. A single cubic centimeter of neutron star material would weigh about a billion tons. The gravitational field at the surface of a neutron star is roughly 2 times 10 superscript 1 times stronger than that on Earth. This immense gravity can cause extreme time dilation, a general relativistic effect where time moves more slowly near the neutron star than it does farther away. Neutron stars have a layered structure with extreme pressures and densities increasing toward the core. The outer layer of a neutron star, called the crust, consists of highly dense, degenerate matter, mainly iron and nuclei crushed by gravity. As one moves deeper, the density increases and free neutrons begin to appear. Beneath the crust, the outer core consists of superfluid neutrons and some protons and electrons. The neutrons are formed by protons capturing electrons under extreme pressure. The structure of the inner core is less understood, but it may consist of more exotic forms of matter, including hyperons, pion condensates, quark-gluon plasma, or other forms of degenerate matter that exist under extreme pressures. Neutron stars often have incredibly strong magnetic fields. These fields are believed to be generated during the core collapse, as the original star's magnetic field is compressed into a much smaller space. Neutron stars have magnetic fields between 10 and 10 superscript 1 superscript 2 Gauss. Earth's magnetic field, by comparison, is about 0.5 Gauss. Some neutron stars have even more intense magnetic fields, reaching 10 superscript 1 to 10 superscript 1 Gauss. These stars are called magnetars and are known for violent bursts of gamma rays and X-rays caused by the decay of their magnetic fields. Neutron stars often rotate at extremely high speeds. When the progenitor star's core collapses, the neutron star inherits the star's angular momentum, causing it to spin rapidly. Newly formed neutron stars can rotate several times per second, with rotational periods as short as a millisecond. Some slow down over time due to energy loss, but many neutron stars maintain high rotation speeds throughout their lives. Some neutron stars are observed as pulsars, a type of neutron star that emits beams of electromagnetic radiation, usually radio waves, from their magnetic poles. As the neutron star spins, these beams sweep across the sky, and if one of the beams points toward Earth, we observe regular pulses of radiation, similar to the way a lighthouse appears to blink on and off. Millisecond pulsars. These are neutron stars that rotate hundreds of times per second, with periods as short as 1.4 milliseconds. They are thought to have been spun up by accreting material from a companion star. There are various classes of neutron stars based on their properties. Radio pulsars. These neutron stars emit regular pulses of radio waves and are detected by radio telescopes. The regularity of their pulses makes them precise cosmic clocks. Neutron stars that accrete material from a companion star can emit X-rays as the infalling material heats up. This process is common in binary systems. As mentioned, magnetars are neutron stars with extraordinarily powerful magnetic fields. Their fields are so strong that they can distort atomic structures and affect the space around them. Some neutron stars do not have detectable pulses or companions. They are relatively quiet, emitting only faint X-rays or gamma rays. The immense gravity of neutron stars can bend light, creating noticeable gravitational lensing effects. Light from nearby stars or objects is bent as it passes close to a neutron star, allowing us to see around the star in unusual ways. According to Einstein's general theory of relativity, time passes more slowly near a neutron star due to its intense gravitational field. This effect is measurable in binary systems and can affect the timing of pulsar emissions. Many neutron stars exist in binary systems, where they orbit around a companion star. In some cases, two neutron stars orbit each other, and over time they lose energy through the emission of gravitational waves, eventually spiraling together and merging. When two neutron stars collide, they create an intense gravitational wave signal and release enormous amounts of energy. These events, called kilonovae, also produce heavy elements like gold and platinum through a process known as R-process nucleosynthesis. Neutron star mergers were first directly detected through gravitational waves by LIGO and Virgo observatories in 2017, GW 170817. These observations confirmed neutron star mergers as a source of gravitational waves and provided new insights into the nature of neutron stars. After formation, neutron stars are extremely hot, with surface temperatures around 1 million Kelvin. Over time, they cool by radiating thermal energy. Neutron stars initially cool by emitting neutrinos from their cores. As they cool further, they emit X-rays and other electromagnetic radiation. The core of a neutron star is thought to contain superfluid neutrons, a state of matter where particles flow without resistance. This superfluidity affects how the star cools and rotates. Neutron stars exhibit some of the most exotic and extreme physical phenomena known, including superfluid neutrons. Neutrons inside a neutron star's core may exist in a superfluid state, which allows them to flow without friction. This affects the star's rotation and thermal properties. Neutron starquakes. Crustal movements, or starquakes, can occur when the crust of a neutron star adjusts to changes in rotation or magnetic field strength. These events can cause bursts of X-rays or gamma rays and are particularly common in magnetars. Glitches. Sometimes a neutron star's rotation speeds up unexpectedly in events known as glitches. These glitches are thought to result from interactions between the superfluid interior and the crust of the star. Neutron stars provide a natural laboratory for studying extreme physics. Testing relativity, neutron stars, especially in binary systems, allow astrophysicists to test predictions of general relativity under extreme conditions. Probing dense matter physics. Studying neutron stars helps scientists understand the behavior of matter at nuclear densities, a regime that cannot be replicated in Earth-based laboratories. Mergers between neutron stars have provided crucial data for gravitational wave astronomy, allowing us to probe fundamental aspects of gravity and the origins of heavy elements in the universe. PSRB 1919+21. The first radio pulsar, discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish, marked the first confirmed detection of a neutron star. PSR J0348 plus 0432, a binary system containing a neutron star and a white dwarf. The system has been used to test the predictions of general relativity. Crab Pulsar. Located in the Crab Nebula, this is one of the most studied neutron stars and is associated with a supernova explosion that was observed in 1054 AD. GW 170817, the first observation of a neutron star merger through gravitational waves, detected in 2017. Neutron stars, with their dense matter, extreme gravity, and unique properties, remain a key focus of research in astrophysics, providing insights into both the life cycle of stars and the fundamental laws of physics.